let's try solving this system with an approximation. So I will introduce you to Bethe approximation. And it's very hard to understand it, so that I have warned you. Okay, so I will be really quick. Okay, now here is, and we are trying to understand, trying to solve Ising model, not necessarily 2D. Actually, in the first order Bethe approximation, we will just solve it. We will just think of a spin at the center. Okay, then it has several spins in its neighbor, S1, S2, S3, S4, and we will just focus on this, and we will assume that everything else is just fluctuating around it. Okay? So we will actually think of it this way. If the system is already magnetized, there is some effective field H that is acting on these spins. Okay? Just like magnetic field, there is an effective field that's acting on them. And if you are going to write the energy of this system, then it is basically minus J times S0, S1 plus S2 plus S3 plus S4, and minus H times S1 plus S2 plus S3 plus S4. First of all, did you understand it?
What is
H is, you know, it's fluctuating around, like, right? Let's say it has created at the periphery of this thing that we focused on. At the periphery, it has created an effective magnetic field. So maybe spins are aligned at the periphery, and they are creating this H. Okay, H will be a parameter, and we will get rid of it at the end with a trick. So far, so good? Do you see how simple this system is? Yes? Very good answer. So you only have, first of all, you have to notice right away here that we are not solving 2D square Ising model. It's just one spin with 4 neighbors. Could have been 2D Ising model, could have been diamond, right? Diamond atoms also have 4 neighbors. So it's not, this model is already wrong, okay, because it doesn't have all the spins. It's an approximation, because diamond lattice and square lattice gives different results. But this gives the same result for both of them. So how would you solve it? You would go over all the possibilities of S0, S1, S2, S3, S4. So 2 to the 5 possibilities, right? 2 to the 5 possibilities. Get the energy for each one of them. Get the probability for each one of them, right? E to the minus EI over KBT. Divided by the partition function, right? Multiply it with magnetization for each state, and you get yourself a result. Well, if you do that, you actually can do that with pencil and paper, and you get very nice cosine hyperbolics and whatnot. Brilliant. Okay, but we will do it with a code. Here is our code. This is Bethe approximation, and we will come to these things soon. So what do we have here? Magnetic field is 0. I have this H, which goes between minus 4 and 4. Of course, I didn't tell you what's the point. Let me tell you what's the point. The point is that you are going to get some expectation value for S0, for the central spin. How are you going to get that? P probability of being at that state, let me call it Pi, and multiplied by the value of S0 at that state. So you have 2 to the 5 states. At each state, S0 has some value, +1 or -1, right? You are going to sum up all the probability of being at that state multiplied by the S, okay? Then, wait for it. You are going to say that I can also calculate this one, right? Yes? Then you are going to say that this must be equal to that. Now, why is that? Let me tell you why. Translational symmetry. Okay, I have an infinite spin system, right? I'm looking at a certain place, and where I'm looking, the central spin is at the center, and it has some peripheral spins, right? But if I jump on top of the peripheral spin, then that spin is at the center, and it has some peripherals around it, right? So the expectation value for the central one and for the peripheral one should be equal, okay? I will go quickly. If you don't understand, just let it be, okay? But ask questions. I want to show you just one thing at the end with this. Look, do you see? I go from S0 between -1 and 1, S1 -1 and 1, right? Hamiltonian J times S0 times blah, 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 right? And then H times this, yes? And then I have here something like I'm going to eventually calculate expectation value of S0. So I'm calculating S0 times the probability of being at that state. Are you following a little bit? Yes. So as I'm changing H, I'm calculating all this partition function and dividing the expectation values. What I eventually plot is expectation value of S1 minus expectation value of S0. What I want to get 0, because the two should be equal to each other. Let me just plot it. I'm plotting it for low temperature first. So I have effective peripheral field versus, peripheral spin expectation value minus central spin expectation value. And this is peripheral field. Do you see that it crosses over here, and at the center? Let me increase the temperature so you see the crossings better. Do you see the crossings better? Now, which one of these crossings? You have 3 crossings. Only 2 of them are okay. Only 2 of them are stable. Let me tell you why. What do you expect to get with the peripheral spin if you increase the peripheral magnetic field? You expect peripheral spin to also increase. Okay? And this is happening here. Right at that point, when I increase this one also increases. So that's a stable equilibrium. Also, this one is a stable equilibrium. Okay? And then, as I increase the temperature, let me increase the temperature a little bit. You might think that nothing changed, but let me go all the way to 2.4. Do you see where it is going? They are getting closer. So at low temperature, you have 2 stable fixed points, okay? And they are getting closer to each other. And at some point, around 2.8, you reach to this stage where they are really close. 2.88, it's going through that thing right at the critical point, where the middle one now becomes stable. So at 3, it is stable. Do you see it? You might be thinking, okay, this is just a quirk, something, irrelevant thing, not important, blah, blah, blah. But if you ask a physicist what is the most important thing, she will tell you symmetry. What is the next most important thing? Symmetry breaking. Okay? This is everywhere. This kind of stuff where you have, we have seen already this with Prandtl-Tomlinson model. Do you remember? When it's this, like this, it's just following, then there's a spontaneous symmetry breaking. Similar kind of thing is happening here. Actually, what we are plotting right now is part of this catastrophe theory. Look, if you plot that thing that goes like this and just follow it in 3 dimensions, right? Like it starts like this, then it gets smaller and smaller and smaller, and then it becomes like that. This thing actually inspired the last painting by Salvador Dali. Do you see this? It's what we are talking about right now. Okay? Remember, computation, physics, blah, 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 art, it's all connected. That was the point. So, Bethe approximation is an approximation, and here I have a very nice code that actually takes this from certain temperature to a certain temperature, follows those routes. You can analyze this code. This is a thing of beauty, indeed. And if you run this code, you are going to get this first order Bethe approximation. Do you see how nice it works? Yes? And what is this one? This is the exact solution by Onsager, right? This is the exact solution for square Ising model. It doesn't need to fit that because Bethe approximation doesn't see the lattice fully, right? Then why don't we go to second order Bethe approximation, right? I know I've lost you completely. This is not the main point. I will come to the main point. Metropolis, that's the main point. I'm coming there. But if you want to go further with Bethe approximation, let's say you want to go further and you want to start seeing the square lattice. So far we did this, right? Let's put also these guys. Now it's a square lattice, right? It's not diamond that goes like that. Now it has these interactions. But the thing is that what these peripheral spins see and what these peripheral spins see are different, right? So now we have 2 parameters, h1 and h2. Now we vary 2 parameters and find the expectation value of this one, and this one, and make them equal to each other with a very nice code, which is over here. You can investigate this code. Do you see? This time there are 9 spins, and we are changing each one of them, and we are writing the relevant Hamiltonian and whatnot. Then if we run this, it will give us the result. Do you have any questions? So, did this make any sense to you? That's an important thing. It will come up in the later stages of the course, at irrelevant places. Okay? I think we can call it a bifurcation, where you have two solutions, one unstable solution, then they come together and you have a single solution. You see, we have improved. We got closer to square lattice by including second order approximation. The thing is that no matter how much you do this approximation, how far you take it, you never catch this one. Never ever. Okay? To really get this one, you need to be on Sagar. Okay? All right. Now the nice part, the Metropolis algorithm. You can go. This was the original part. Okay. So, let's talk about Metropolis. Do you have any questions? Was this clear? I
might ask something at the end.
Okay. So, here's the thing. Let's say you have n by n spins, right? N by n. So how many states do you have? 2 to the power of n squared, right? Very hard to deal with that many states. What do you do with those states? You choose one of them. You choose one. Choose one, let's say at random. Let's say you have an algorithm. You want to get the ultimate result, but instead of going over everything in the model, you say that why I don't choose at random, okay, and do the statistics from the randomness, okay? The thing is that you choose at random and you multiply by e to the minus e over kbt. What will happen is that if you are already choosing at random, you will mostly sample high temperature part, like the highly disordered situations. Do you agree with this? For example, if you are at low temperature, the system will hang around at at the ordered stages, but you are trying to get some property and you are just summing over all those disordered stages which has very low energy, very low probability. Makes sense or not? Oh my God, you are so... Hocam, are you following? Yes? Yes. So, good. Let me tell what would be your solution to this problem? There's a super easy solution that Metropolis came up with. So we are choosing at random. We are multiplying with e to the minus e over kbt. We are going to flip this backwards. We are going to choose with this probability and then take the average. Do you understand? So okay, let me explain. So Metropolis tells you that take a spin state and then flip it. Let's say we flip this one. How much energy will be changed? What is the change in the energy if I flip it? It was like this, and I flip it. What is the change in the energy? Can you tell me? Okay. Up, blah, 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 blah. What is the energy now? You don't know? Minus? Let's say minus 4J, because there's this interaction, this interaction, this interaction, and that interaction. 4 interactions, minus 4J, right? What is the energy once it is flipped? Plus 4J, very good. So did the energy increase? Yes. So Metropolis tells you that if the energy increases, then accept that increase with a probability of e to the minus delta E over kBt. So energy increased. How much did it increase? By 8J. So we are going to accept this change with this probability. Okay? When the temperature is very low, this will be a very low number. Do you agree? This time it's actually e to the minus infinity. Okay? So when the temperature is low, we are not going to accept the flips that are increasing energy. What else Metropolis says? If energy decreases, just accept it. Okay? If you do this, you are going to sample the system accordingly. You are going to sample those ordered states at low temperatures much more than they really are. I mean, for example, let's say all spins are up, right? And very low temperature. You want to flip a spin, it doesn't accept it because very low probability, right? You go to the other spin, you want to flip it, doesn't accept it. So the system stays actually in the aligned state. Okay. Now let's increase the temperature. You start from ordered state. You want to flip one of the spins. It actually increases the energy, but kBt is very high, so there is a nice probability of going up. So that way, since also the disordered states are huge, there are a lot of them, you start going towards disorder. Okay? That's what our code is doing. Look, we start with random states. Then right at the beginning, I choose, so one Metropolis Monte Carlo step is the following. You go to each spin randomly. You go to this spin, try to flip it with certain probability, you accept it, okay? Then go to other spin, try to do it until you go over all the spins, okay? That's why I have these n squared random sites. That's where I'm going to try flipping, okay? Then there are n squared random numbers. That's the dice that I'm going to use. And then there is, let's say xy is a certain site. I go there and this is my delta E. Why do you think this is my delta E? Let me show you here. Did you notice when it was up, our energy was minus 4J, right? When it was up. Sorry. The change in the energy was 8J. So let's get the same result. 1 plus 1 plus 1 plus 1 times the 1 in the middle is 4. 4 times 2 is 8. Do you see? 8J. So that's why it's basically the change in the energy is the sum of the neighbors times the central spin. Okay? And this is basically Monte Carlo step. Metropolis's algorithm. It says that if the random dice number is less than exponential e to the minus delta E over kBt, then accept it. Why I don't have this, if the energy goes down, also accept? Why I don't need that part? Can you guess? So when do I definitely accept it? Do you remember? When I was accepting it? When the energy decreased, right? If the energy is decreasing, it means that delta E is negative. If delta E is negative, it means that, I actually have a problem in this code, right? I realized I have a problem in this code. Okay, then let me go back to the original case. If dE is 0 or if this is the case. Doesn't matter. Problem is solved. So that's what you saw before. That's what you saw before. And we already have seen that after certain temperature, you are going to get demagnetized case. There is a faster version of this, but you are bored, so I'm skipping that part. Let's do comparison with theory. So let me run this code. And while it is running, it's going to go over certain temperatures. And for each temperature, it's doing 400 times 10,000 trials. That's flipping. Should I flip it? No. Should I flip it? No, etc. Then it does another 100 times 10,000 of that to get magnetization. Okay, here it is working right now. So this is the critical temperature. This is the exact result. And this is Monte Carlo, Metropolis Monte Carlo. And as you can see, we are spot on. Do you see it? We will not be spot on here because that part is really complicated. That part is like that, indeed, only when you go to infinity. Indeed, when you take n to infinity, which, although Metropolis algorithm is a very nice algorithm, we just simply can't do that here. But so far, do you see how perfect it is? Yeah. So can someone tell me in a nutshell what Metropolis algorithm is doing? What is its advantage? Instead of trying, that's fine. It will come back. Instead of doing 2 to the power of 10,000 calculations, which we can't do ever, okay? Metropolis algorithm lets us focus on what is important. I mean, it lets you sample the system properly. Okay, that was a fluke. I mean, normally it wouldn't go that way. It works. Okay. One final thing that I want to show you. One final thing is this. It's not just for solving this kind of problems. Metropolis algorithm, the idea there is very general. Okay. In many things, in many optimization problems, you can define the thing that you are going to optimize as energy, and you want to minimize it. Let me give you an example. An example is traveling salesman problem. Have you heard of it? No? Traveling salesman. Let's say you have several cities spread out a country. You want to sell something. You want to visit every city once and come back home. Okay? So let's try. Not a bad journey, right? So we are looking for a shortest path. But notice that if you have n cities, then you have n factorial possibilities, n factorial possible routes that you can choose from. It's a hard problem. But you can solve it heuristically. You can solve it heuristically, which is a word. Basically, another word is satisficingly. That's also a word, interestingly. Can I detour? Yes? I usually take this detour here to explain satisficing. Is a decision-making strategy or cognitive heuristic that entails searching through the available alternatives until an acceptability threshold is met. So you just let go your obsessive compulsive part that searches for the best of the best routes. You just say that, okay, I want to get a route that is decent in a decent amount of time. Okay? And it was introduced by Simon. Where are you? Can I go like this? This guy. Do you know this guy? Nobel Prize in Economics? I don't think so. American political scientist. Maybe. Okay, where is his scholar? Yeah. Do you see it? Administrative behavior, organizations, artificial intelligence, human problem solving, this kind of stuff. Okay. Now, back to this problem. We want to find a satisficing solution, heuristics. Okay. So what do? We do the following. Let's say our energy is the path. We want to minimize the energy. We are going to do the following. Notice that whenever you have a crossing, let me take it back. Was it just one path? That's a pity. I want to draw it again, but not as a single path. Okay, let's do this. Sorry. Okay. Okay, there you go. Do you see the crossing? Do you see that? Immediately you see that, and immediately you understand that it's wrong. Right? Because you can always do this, and it will be shorter. Right? So that's what we are going to do. What we are going to do is this. We are going to choose two cities, one city over here, one city over here, let's say. Okay? And we are going to look at their next cities. Okay? If by changing these cities, I can get a shorter path, then I'm going to accept it. Okay? If changing increases the path, okay, I'm going to accept it with a certain probability, depending on temperature. Okay? Now, okay, so what? Where is the optimization? The point here is that we are going to start with high temperature, which will give us the possibility of exploration. We are going to explore many different things because we are relaxed. Can I do that? Yes, you can for now. Can I try that? Yes, you can for now. But then we will decrease temperature. We will be more and more obsessed with not increasing we will not be relaxed. Its exploration stage is over. It's exploitation stage now. Do you know that thing? Exploration, exploitation. It's a typical two words that are used in computer science. You do the exploration, you see all the possibilities, then you come back, you get one result. That's what we are going to do. That's what this code is doing. It's called simulated annealing. Do you know what annealing is, mechanical engineers? What is annealing? Exactly. So you first increase the temperature of a metal so that atoms jiggle and find the excellent places where they can interlock. Then you decrease the temperature slowly so that they stay there and become a perfect metal, right? Which you usually don't want to have. Because when they are perfect, their hardness is bad, right? So you keep hitting it so that you have domains. It depends on your application. Sometimes you want perfect metal. Then you do annealing. This is simulated annealing, right? So let me show you the code. There are some locations, random locations, n of them, and some distances that we calculate beforehand. And then what we do is we think of this. Okay, let me show you. Let's say this is 1, this is 2, this is 3, this is 4. Okay? We will look at the distance 1, 2, 3, 4 versus 1, 3, 2, 4. Okay, sometimes they will be crossed and we will open them. Sometimes they will be open, we will cross them, depending on the temperature and acceptance rate, what the dice comes out, etc. Do you see? 1, 3, 2, 4 minus 1, 2, 3, 4. Yes? Are you with me? Same kind of Monte Carlo stuff. And this is the flipping part. You are literally flipping this root. If you want to flip this root, you have to flip the whole root like that. If you want to untangle it or tangle it, depending on... Okay, here comes. So I start with a random initial point. Temperature is high. I'm trying many different things. In the meantime, I'm decreasing the temperature. And voila, I have solved. This is a heuristic solution, nice, decent solution that doesn't have any crossings. And I'm happy, right? If you did this, yes?
Do you know that this is the shortest route?
No, that's the thing. It's heuristics. So you are okay with not having the global minimum. You are fine with local minimum because you reach there at least in finite time. It seems like a minimum. What we can try is, okay, before that, let me show you this paper, 1983, Science, Optimization by Simulated Annealing. And this is exactly what they did. Do you see? Traveling salesman stuff. All right. Coming back to your question, let me take a screenshot of this one. Okay. And I will run this one more time. But I will not start with different locations, same location. In the meantime, let me take this screenshot so that we are going to be able to compare it. Did it reach the same solution? So which part is different? Ah, this part is different. But it's awesome, right? It's more or less the same thing with a different flavor. You can see that some things are there because they are good ideas. Some things are changed because usually the thing that changes is what happens in the middle, because there are a lot of local minimas there. Good. I think you forgave me for a very boring lecture with this final optimization thing that seemed to be interesting to you. Yes? Good. Yes?
How will we know the best solution?
Let it go. There are algorithms that find the best solution, and usually what they are good for is to just check these algorithms. And nobody cares about really having the best solution ever, except for checking whether your heuristics is good enough or not. I think. Because, the time you spend by finding the global solution, you can just start selling whatever you are going to sell. And usually it's not this simple. There are other things, like very recently there was some problem in this road, so you should avoid that road. So there will be these optimization problems will always come with different complications. So if you are still obsessed with the perfect solution, you will be left behind. Any other questions? Okay, take good care.